So what I forgot to do on our previous video was show you this, and I apologize, I knew I was missing something. So exploring accumulation of change. So we've got the accumulated quantity is equal to the rate 1 times the change in time, plus rate 2 times the change in time, plus blah, 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 rate all the way out to rate n times the change in time. The accumulation of a quantity is represented by the area underneath its derivative curve. So underneath the rate of change, the accumulation is the area underneath the rate of change. You can change those words. I'm actually going to go ahead and do that on my paper in a minute. Units for area underneath the rate of change curve are the units of the rate of change times the units of the independent variable. Area above the x-axis is positive accumulation, snow falling. Quantity is increasing. Area below the axis is negative accumulation, and the quantity is decreasing. So there we are. All right, take a minute, start writing that down. I will too, and then we'll come back together and I'll have some new pieces of information about you. All right, so it's the same thing. I've just rewritten it. Accumulated quantity, rate 1, blah, 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 blah. So I wanted to add something to number 2. The accumulation of a quantity is represented by the area underneath its derivative curve. So that means the derivative curve or rate of change you could also say maybe y prime here, that kind of stuff. So the area underneath the curve. Okay. All right, I don't remember what else I said. It was really quite insightful. I'm sorry I don't remember it. But this is accumulation. So accumulation just means how much is there. So if they ever ask you for, well, how many, there's been some weird questions who will ask about, like, how many people are on the, have taken an escalator? How many bananas have been sold? How many? It's a big deal. It's easy. It's really easy, but it's a big deal. Okay. I don't know why that won't go away. All right, let's move this up and see what we can do to check your understandings. Again, before you do any of the, watch me do this, make sure you pause and try them. So a squirrel starts at building A at time 0 and travels along a straight wire connected to building B. For time between 0 and 18, the squirrel's velocity is modeled by the piecewise linear function shown below, where v of t is in meters and t is in minutes. So they told me what v of t is and what t is. It's important because we're talking about the units. So the area underneath the curve rate, if I want to know the area, the rate of change, or the equation times the rate of the independent variable tx, whatever it is, this axis times the units on this axis, the units of the curve. Okay. So if we think about Janet's snow, okay, it was cubic feet per hour is the graph, and then this is hours, and so the area we find is just cubic feet. Okay, all right. And squirrel starts at the blah, blah, blah. At what time intervals does a squirrel change direction? So if we recall our knowledge we have gained in unit 1, this is v of t is like a derivative because it is a rate of change. It's meters per minute, and that is a derivative. Remember, it's the derivative curve. It said, we just wrote that down. It's the derivative curve. So this is the derivative when a squirrel changes directions, when at critical points, potentially, when it changes from plus to minus or minus to plus. Okay, so let's take a look. It looks like e equals 9 is 0. It goes from positive to negative. What is it? A lot of you use it. Make sure you are saying what it is. V of t changes. Okay, so that's 1. The next one is 15. Again, V of t changes from negative to positive. Okay. At what time is the squirrel the farthest away from the building? How far away is it? Okay. So positive, negative, positive, right? And so we might need some areas here. I'm going to go ahead and find them just in case I need them. So this is 20. That's my height. And this is a trapezoid. Now I can absolutely break this into shapes that make me more comfortable. I can do 2 triangles and a rectangle in between. I'm going to go ahead and use the trapezoid formula just to get us familiar with it. We're going to be using it a lot on Monday. So the trapezoid formula, 1/2 the height, which is 20, times base 1, which is between 2 and 7, so that's 5. And base 2 was between 0 and 9, so that's 9. And so, and height was 20. So 10 times 14. So this area is 140. Okay, then down here, do another color. My height is 10. Base 1/2. It goes from 9 to 15. 9 to 15 is 6. It goes from 10 to 14, that's 4. So I've got 5 times 10, which is 50. And again, area is going to be meters squared. No, it's going to be meters. Thinking area, so it has to be squared, but it's meters per minute times minutes, because these are minutes. And so it's just meters. And then we have this last part. We have an imaginary line right here. It's not really there. But my height is 10. And my base 1 is from 16 to 18, so 2. And from 15 to 18, so 3, which is equal to 5 times 5, or 25 meters. Now, one thing to keep in mind is that this one is negative because it's down here, and these two are both positive. So when he's at the farthest away. So he's traveled 140 meters in 9 minutes. Then he goes backwards, and now he's only 90 meters away. Then he goes forwards. So I'm going to say time t. T equals 9. He's 140 meters away. Because the rest of this is going to take away from that, make it 90 meters away. Amazon dismiss. All right. And then, like I said, so backwards, so it'll be 90 meters away. Then it goes 25 more meters away, and that's 115. So he's definitely farthest away at time 9. Okay, but I did make sure by doing all that math. So the only math I had to do was actually this, and it's pretty clear that he's traveled the farthest in this time, the biggest area. This area is clearly smaller. That area is also clearly smaller. That kind of stuff, but it's important to kind of think it through. All right, let's see our last question. The flow of oil in barrels per hour is shown for a particular day in July, which is the best approximation of the total number of barrels of oil that passed through the pipeline that day. So we're going to guess. So this is the total number, the flow of oil, okay? And so the area underneath this, and I'm going to break it into 4 sections, is going to be this one. This, probably that's the best way to cut that. So I can treat this as one big rectangle down here plus a triangle on top. That's good. And try to figure out the area. So 6, this is 6 times 100, so this is 600. And there are 4 of those. And then what are those? Add them up. See what you can do. Answer is D. 600, 600, 600, 300, 300 is, it's really 6 times 5, so 3,000. Okay, I'll talk to you guys soon. Have a great weekend.